All right, lipid metabolism going farther. So reviews of some of our key terms: CoAsh, acetyl CoA, and acyl CoA. Acetyl CoA down here. That is our coenzyme A plus an acetyl group. Acyl CoA is a fatty acid chain linked to coenzyme A via a thioester bond. Now, fatty acid synthesis and biosynthesis, we've talked about a little bit. We've talked about it in kind of a simplistic manner. Now, what are some of the fates of acetyl CoA? Glucose is first degraded pyruvate through glycolysis in the cytoplasm. Pyruvate is transported into the mitochondria where it's decarboxylated and converted to acetyl CoA and other products. Now, acetyl CoA can do a number of different things. It can serve as a substrate for citrate synthesis and complete the citric acid cycle, electron transport chain, and oxidative phosphorylation. So you can take an acetyl CoA molecule and basically rip it to shreds and get a bunch of ATP out of it. Or if there's excess citrate citrate can be transported out of the mitochondria to the cytoplasm to generate oxaloacetate and acetyl CoA for fatty acid synthesis. So if there's too much citrate, then you're going to go in the route of fatty acid synthesis. Now, fatty acid biosynthesis occurs primarily in the cytoplasm of the liver. Okay, now this is an important thing to think about. If the degradation takes place in the mitochondria and the synthesis takes place in the cytoplasm, they're divided. Those two different things don't have to worry about, well, basically one person building up and the other person breaking it down. You don't have to worry about those things, coming to a head and causing a problem. Fatty acids are synthesized when the diet is low in fat and or high in carbohydrate or protein. Most are synthesized from excess dietary carbs, example, glucose. Processes combining 8 2-carbon fragments, acetyl groups from acetyl CoA, to form a final 16-carbon fatty acid named palmitate. Palmitate can be modified to give rise to other fatty acids. It can be, the chain can be elongated, or it can be desaturated. Yeah. Now, a fatty acid biosynthesis overview reaction looks something like this. 8 acetyl CoA molecules plus 7 ATP plus 14 NADPH and protons yields palmitate, 8 CoAsh, 7 ADP and PI, 14 NADP, and 6H2O. A large quantity of NADPH is needed for fatty acid synthesis, mostly provided through the pentose phosphate pathway. So a large quantity of NADPH is needed for fatty acid synthesis. So if you were curious, well, why do we do the pentose phosphate pathway? Well, so that we can generate this, so that we can do fatty acid synthesis. Now, step 1 takes an acetyl CoA molecule and uses the enzyme acetyl CoA carboxylase. And what that's going to do is take this methyl group and simply add CO2 to it. So we're going to make malonyl CoA. This is the first product generated from the hydrolysis of ATP with the enzyme acetyl CoA carboxylase. So this is going to require ATP and biotin. Now the activating reaction is necessary because step 2 is this is an activating reaction. Step 2 is thermodynamically unfavorable. This is a rate-limiting step of fatty acid synthesis. So in fatty acid biosynthesis, we have all of the remaining reactions done by an enzyme complex known as fatty acid synthase. This is a very large complex. It is a dimer arranged in a head-to-tail configuration. This is almost like what we talked about with the citric acid cycle in a metabolon, but it's not quite the same because we have a limited number of enzymes. So 2 fatty acids can be constructed at the exact same time. Now, step 2 of this, acetyl CoA transfers an acetyl group to acyl carrier protein, or ACP, to form acetyl ACP. This is catalyzed by a transacylase. Step 3A, acetyl ACP transfers acetyl group to synthase to form acetyl synthase. This is catalyzed by a transacylase. Step 3B, malonyl CoA, if you remember the product from our very first reaction, transfers the malonyl to the acyl carrier protein to form malonyl ACP. This is catalyzed by malonyl transacylase. So what we have here is we've got our acetyl CoA. Then we make our malonyl CoA. So that is done right here. We've already talked about that and visualized that. Now what we have to do is take these guys right here and transfer that to our acyl carrier protein. So simultaneously, while that's happening, we have an acetyl CoA molecule where a transacylase is going to take that acetyl group and make acetyl synthase. So what we have now is acetyl synthase and malonyl ACP. That malonyl ACP and acetyl synthase are going to make acetoacetyl ACP and CO2. This is catalyzed by a synthase enzyme. Step 5, we're going to take the resulting acetoacetyl ACP, so to produce beta-3 hydroxybutyryl ACP. This is catalyzed by a reductase, and this requires 1 NADPH. Step 6 is going to take beta-3 hydroxybutyryl ACP to produce crotonyl ACP. We're going to remove 1 H2O in the process. This enzyme the enzyme that does this is a dehydrase. Step number 7 is going to take crotonyl ACP to make butyryl ACP. This is catalyzed by reductase and requires 1 NADPH. This is now a fully saturated 4-carbon long fatty acid chain. So you might be thinking, this is a lot of work. What did we do? Well, we first had to get our acetyl CoA molecule. We had to make malonyl CoA. Then what we had to do was take those carbons and throw them onto our acyl carrier proteins so that we could really get moving through this. Now, what we just described started with acetyl synthase and malonyl ACP. So our carbons from our malonyl CoA are now on the acyl carrier protein. Acetyl synthase is going to allow us to use the enzyme beta-ketoacyl ACP synthase to produce acetoacetyl ACP and decarboxylate this. So what we're doing is we're basically modifying what we've added to our acyl carrier protein with the end goal of getting this chain right here. So I think that if you look at our carbonyl carbons here and here, this one that I'm putting the star by, that's the one that is going to stay next to our sulfur, or our sulfur. This one right here that I'm putting simply a plus by, ultimately we have to get rid of that. So how are we going to do that? Well, first we're going to reduce it. We're going to use beta-ketoacyl ACP reductase. So we're going to add a we're going to add a hydrogen to that oxygen, then we're going to add a hydrogen to that carbon. Okay, now what we need to do is we need to remove that oxygen, and we're going to use a dehydrase enzyme to remove a full H2O molecule. Now once we've got that beta-3 hydroxyacyl P dehydrase, we've got a double bond within our carbon. We don't really want that. We don't want this crotonyl ACP. So what we're going to do is we're going to reduce that double bond and in effect remove that. So now we have a fully saturated 4-carbon long fatty acid. It's a lot of work when the drawing of it is pretty simple. The drawing conversion is very simple to do. Just, well, where there was a double bonded oxygen, drop the double bonded oxygen, put 2 hydrogens there. Done. Not quite the case. You have to remove it step by step by step. All right, so the cycle is repeated over and over and over again until you form palmitoyl ACP, 16-carbon long fatty acid. So we just repeat that over and over, slowly but surely elongating our fatty acids. Now, thioesterase hydrolyzes palmitoyl ACP to palmitate. So this enzyme right here, thioesterase, is what is going to release the palmitate, our fatty acid. Once that has been released, now our synthesis is complete. So we started up here at the top, and we went all the way through, repeating a number of these steps 6 times, 6 elongation cycles, until we got a 16-carbon long fatty acid. So reaction number 1, acetyl CoA carboxylase, that is taking your acetyl CoA and adding a carbon dioxide to it. Reaction number 2, everything after that is done by the fatty acid synthase complex. So there's a ton that's done by the fatty acid synthase complex. And remember, this can be done simultaneously, 2 times at once. So here is what fatty acid synthase looks like. Now, the cool thing about this is this display right down here that my head is partially blocking shows the movement of all of the different components. So we had all these different enzymes, but what we've got is all of these different functions that are kind of detailed here. So KS, MAT, DH, ER, KR, and TE. Beta-ketoacyl synthase, malonyl acetyl transferase, beta-hydroxyacyl ACP dehydrase, enoyl ACP reductase, beta-ketoacyl reductase, acyl carrier protein, and thioesterase. So basically, it's almost like that's a big factory that takes the substrate and starts with it over here, moves it over here. Well, now after it's over here, it needs to go over here for this function. Then up here, I just kind of think that it's like this really cool assembly line where this molecule is just being passed around over and over again. Here's something done here, something here, 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 here. That's a pretty cool, well-orchestrated system. Now, fatty acid elongation and desaturation. Now, both of these, so adding some double bonds. Well, going from a 16 carbon long completely saturated fatty acid, what can you do? Well, you can use endoplasmic reticulum enzymes that are going to, well, manipulate these fatty acids. Now, this is a very important part in regulating membrane fluidity and synthesizing precursors for other fatty acids. So I think that this is maybe the most important compare and contrast for fatty acid metabolism. On the left-hand side, we've got beta oxidation. On the right-hand side, we've got fatty acid synthesis. The first thing that is important to point out and to recognize and appreciate is where these things are taking place. Subcellular location of beta oxidation in the mitochondria. Synthesis in the cytoplasm. What are the substrates for this? Well, for fatty acid synthesis, you've got acetyl CoA and NADPH. Okay. Now, your substrates for beta oxidation, you've got acyl CoA, FAD, NAD, and CoAsh. Your products that you're going to be generating from fatty acid synthesis, you're going to get palmitate, NAD+, CO2, and CoAsh. Your products for fatty acid oxidation, you're going to get acetyl CoA, FADH2, and NADH. Now, the overall look of what's happening in beta oxidation is you've got this molecule right here. And we've just been given an R group there to indicate that, well, it could be 6 carbons longer, it could be 3 carbons longer. But essentially what we're going to do is we're going to take FAD and FADH2 in this redox reaction to put a double bond in. Then we're going to hydrate that double bond. Once we've hydrated our double bond, we've got an oxygen or a hydroxide group and a hydrogen on that carbon. So now what we need to do is another hydration, we need to remove 2 hydrogens, so this hydrogen and this hydrogen, to give us this double bonded oxygen. Once we have that double bonded oxygen, we can bring in CoAsh, and now all of a sudden we've got 2 acetyl CoA molecules. Now, as it turns out for fatty acid synthase, starting with these 2 carbons on our acyl carrier protein, or our malonyl CoA, what we're going to do is a condensation reaction where we've added 2 carbons onto the 2 carbon long molecule that we already have. We're going to do a redox reaction, we're going to do a dehydration and a redox reaction, and end up with a fatty acid that's longer. So if you look at the sequence of events, we've got redox, hydration, redox, cleavage. Condensation, redox, dehydration, redox. There are some things that are not radically different from one another. They're kind of the opposite of one another. But a key part of both of these processes are redox reactions. So I hope that this was helpful to kind of visualize what's happening and recognizing that in both cases, it's kind of a piecemealing of breaking down these molecules, 2 carbons at a time, 2 carbons at a time, 2 carbons at a time. All right, well, I hope this is helpful, and I will, yeah, that's the end of the exam 4 stuff.